Hello, you absolute legends. My name is Don Cavanaugh, and I want to talk about predicting physical properties of hydrocarbons. The physical property that we're going to be trying to predict or compare between hydrocarbons is its boiling point or melting point, which are both related to the molecular weight and type of interactions that are occurring between molecules as they make those respective phase transitions. The first thing, and I'm talking about hydrocarbons, so molecules that contain mostly hydrogen and carbon. The first thing to consider is the molecular weight or the number of carbons that are present in the molecule. Through here, I have the numbers 1, 4, and 16, and then kind of on to infinity. Hydrocarbon chain lengths, the number of carbons, if you look at a formula as it's written, the longer the hydrocarbon chain, the more you would predict for it to be solid or liquid and have higher boiling points and higher melting points. And the opposite end is true right here. In fact, if you see a molecule that has 4 or less carbons and there's not anything else going on in there, it's a good indication that that's a gas or a liquid. Propane, butane, ethane are examples of carbon chains that are very small. Butane is just 4 carbons and it is a gas. Liquid, when you get between 4 to 16 carbons, or 5 to 15 carbons, you start getting into things that at room temperature are liquid phase. So hexane, which is a 6 carbon molecule, and petroleum, which are combinations of like 8 to 14 carbon molecules, gasoline, petroleum, kerosene, these are liquid at room temperature. Volatile and combustible, the fumes are volatile, but they're still liquid at room temperature. And if you get longer carbon change, you start getting into 15, 16, 17. We're talking about oil, grease, wax, paraffin, petroleum jelly, things that are standard to be solid at room temperature. If you have two molecules to compare, first thing you evaluate is the number of carbons that are present and the molecular weight. The higher the number of carbons, the higher the molecular weight, the higher the boiling point is going to be, the higher the melting point is going to be. If you have molecules that tie, let me see here. Let's say you have molecules that tie on their number of carbons and the molecular weight. Then you evaluate these things here. Things that will increase the boiling point and melting point are the number of functional groups that are on that molecule. And here I try to have 4 examples of functional groups drawn here. Now, note that these contain oxygen, nitrogen in different bonding ways. Here is a double bonded oxygen, single bonded oxygen. This is formic acid. Now, it contains 1 carbon. So if we start with our analysis here, 1 carbon going to be a gas. But if we look forth to number of functional groups, it's like, hey, this thing has a lot of potential to interact with other molecules that contain these unique functional groups. Formic acid is actually a liquid at room temperature because these interactions between hydrogens and hydrogen bonding and lone pairs are holding the molecules down, requiring a higher melting point, a higher boiling point. The last thing to kind of consider now, the number of interesting things you see on a molecule, interesting things being not carbon, not hydrogen, anything other than carbon and hydrogen is interesting. The more interesting things you see on it, the higher the boiling point and melting point can be predicted to be. The more carbons, the more functional groups, those things will increase the melting point, boiling point. Things that decrease the boiling point, melting point, short, light, small molecules, lots of branching. What is branching? Here is a molecule that contains 7 carbons, and there's a special prefix we use to specify 7. It's the same as the regular polygon. This molecule contains 7 carbons, and it has a boiling point. I don't know what it is, but if I increase the branching, meaning that this molecule still has 7, this is going to have a lower boiling point than if it was just a straight chain. This is going to have a higher boiling point, a higher melting point. Here's a branch that's going to be a lower melting point, a lower boiling point. If it were to branch again, this would be lower melting point and lower boiling point still. If you have any questions, please post them. Have a great day.